So we're just going to do a kind of a short video, honestly, a really short video on taking derivatives of functions when you do not have a base of e in an exponential. So let's go to this. I just wanted to do a couple of quick examples, but to remind you, if you ever take the derivative of something of the form e to a power, e to the u, you would take e to the u, the original question, multiplied by the derivative of u with respect to x, which is that exponential piece. So, for example, if you were going to take the derivative of e to the x cubed plus 2, you would get an e to the x cubed plus 2, but then you'd also need to simultaneously then multiply by the derivative of that exponential piece right here, which is going to give us 3x squared. Hopefully that feels somewhat comfortable to you guys. I think we've done that reasonably well. But now we want to go ahead and go on a little bit further and talk about what happens when we take the derivative of something that is of the form a to the x. Well, it's not particularly difficult, and it's not that much different than what we had before, but you would have a to the x just like before. But the way that I say it is I would multiply like by a penalty, the natural log of a. And so as such, then the rest of that happens. Now, keep in mind, chain rule is still going to apply because it always applies in the same way that PEMDAS always applies. Order of operations applies through all levels of math. In calculus, anytime you have a composite function, a chain rule is going to play. So a simple equation here. The derivative of 7 raised to the 5x plus 2, it's always going to get that piece back, no matter what happens. When you take the derivative of an exponential, the original question comes home. That's sitting right here. Every single time you have a question, that original exponential is part of our story, but then we need to multiply by a couple extra pieces. One is the natural log of 7 because this problem did not have a base of e. The other one is because this is a composite. Right here, this composite had a 5x minus 2 in it, so the derivative of 5x minus 2 is 5. So that's a lot of little pieces, but that's the end of our story. Number 2, let's go a little bit further. Y equals x squared minus 3. And we're going to multiply by that to 4 to the 2 take away x. Now, I purposely tried to do one problem that had a couple of extra little pieces in it. I would think of this as f and this as g, of course. This is a product rule. So y prime would be f prime g plus g prime f. And so let's see what we've got. F prime is fairly simple. It would be 2x. Times g itself, which is 4 to the 2 minus x. Hopefully I didn't write that too poorly. Plus, now we're going to have g prime times the original f itself. But g prime is the part that I'm the most concerned about. So we're going to go through the process like we did over here. If I take the derivative of 4 raised to the 2 minus x, I'm going to get that original exponential back as it's stated. I need to multiply by the natural log of 4 because I have my little penalty for not using the proper base. And then one last piece, I need to take the derivative of the exponential itself, and the derivative of 2 minus x is negative 1. Now, that is, in a sense, the whole story, but one thing that is nice to do at times, at least, is to recognize that in these type of stories, since this 4 to the 2 minus x seems to be repeating itself throughout the question, it's fairly typical for people to go ahead and factor that out. And so we might go ahead and rewrite the problem as 4 to the 2 minus x. I might put a 2x for this first term. I would have a negative natural log of 4 right here with this x squared, and a negative natural log of 4 with this part right here, which is the 3, which again, I guess I could put a plus because there's a double negative times that 3, which I would have preferred to write the 3 in front, but I'm just trying to go a short video, so I'd probably call that 3 ln 4. And that's really all I can do with that problem. So number 3, go ahead and make one just a little bit tougher. If we had 4 and we wanted to raise that to the xy power is 2x squared. Now, I wanted to give you one product rule problem, and I wanted to give us one that involved an implicit derivative because x's and y's are together. So if we took the derivative of 4 to the x plus y, remember, anytime you take the derivative of an exponential, you get that exponential piece back. So you get that 4 to the xy back, but then we have to multiply by the derivative of the base, of the exponent, excuse me. So f prime g, so the derivative of x is 1, times g, which is y, plus the derivative of y, which is dy dx times the first. So that is the derivative of the left side of my story, and the right side of my story is fairly benign. I just have 4x. Now, one of the nice things I will say about problems like this at times is we do have a little bit of a story right here that 4xy is 2x squared. So you see this 4xy that's sitting right here? That 4xy could explicitly be changed to 2x squared. And that actually kind of makes the problem a little bit easier as we go through this, because if I were to divide both sides by 2x squared, because I could, I still have my natural log of 4 over here. In fact, let's go ahead and distribute that. So we got a natural log of 4 times y, plus x ln's of 4 times dy dx. But if I divided both sides, I would just have 2 over x. And so now the process of kind of stripping it away and getting it all by itself is a little bit nicer. So we are going to have our 2 over x minus ln of 4 times y. And then my x would just be 2 over x minus ln of 4 times y divided by x times the natural log of 4. I suppose it might be smart for us to do one last step, which would be to multiply everything top and bottom by x. This is dy dx, right? So sorry about that. Let's multiply everything by x, and I'd get 2 minus x ln 4y over x squared ln 4, and that would be my final derivative. I knew that was a little bit too high up there for it to hold on to what was happening. Okay, last question, I think, for this would be question number 4. And I was just going to go ahead and embrace chain rule a little bit harder on this problem. I've noticed that not everybody's having a difficult time with this, but a few people are. I wanted to look at a chain rule that had a few layers involved in this. So one of the encouragements that I've given you guys is that when you see something like a tangent cubed, what I'd love to see you do is rewrite it as a tangent that is being cubed that way. They mean the same things, but it's explicitly written a little more clearly when we write it this way, because if we do anything to the third power, that derivative would be that thing raised to the second power. And we leave the interior portion unchanged. So I'm going to use a highlighter. Notice I took the derivative of the 3 part. Now I need to attack the next part as I work my way from the outside of the function in. The next piece is going to be the tangent itself. The derivative of a tangent itself is a secant squared. Notice again, I left the interior piece alone. Now I'm going to work a little bit further in, and I'm going to get to the 6 portion. The 6 would be the third step. It's 6 to the power. So I think what we know is that the derivative of any exponential is that exponential itself multiplied by, I'm going to run out of room, we're going to multiply that, so that's down here, it's all multiplied by this thing right here, the natural log of 6, because we were not in base e, and times the derivative of that exponent portion, which is my final piece, times 5. Now, in this particular story, there's not a whole lot I could do to make this problem better. I mean, I suppose I could put the 5 and the 3 and the natural log of 6 in front and call it 15 ln 6. We could probably make it look a little bit better by calling it a tangent squared, just like the secant squared. But then we're all the way down to our final answer, and there's really nothing else I can do to make that problem look any better. I think I called that number 5. It was actually number 4 because I have a fourth problem that I chose not to do because I wanted to keep the video relatively short. So hopefully that's helpful. I will see you back in class. Bye-bye.